RC circuits are undoubtedly one of the most fundamental systems in electronics. For essentially all time-related electronic circuits, capacitors and resistors are often found together, relying on one another to serve a purpose. And while they work extremely simply on their own, things start to get a lot more difficult when they start interacting with each other. So, in order to understand the true physics of RC timing, we first need to gain a fundamental grasp on the formulas that govern the behavior of both capacitors and resistors. The ability for any capacitor to hold charge is given by the equation C is equal to Q over V, where C is capacitance, Q is charge, and V is voltage. In other words, 1 farad is equivalent to 1 coulomb per volt. This denotes that for every volt gained, the capacitor receives enough potential difference to retain an additional coulomb of charge. Now, before we understand RC circuits, let's connect a theoretical capacitor of 1 millifarad to an ideal 50 mA constant current source. After 1 second, what will be the voltage of the capacitor? If we work in differentials, or tiny changes, we can rewrite the original formula as a function representing the capacitance of a capacitor as it changes in time. This can be represented as the derivative of its charge with respect to voltage, both as functions of time, which can then be arranged to this. If we take the formula for electric current, which is I equals Q over T, and work in the same way, we get this equation. This represents the rate of change of charge with respect to time. Since we previously defined the change in charge equal to the capacitance times the change in voltage in our original formula, we can substitute the variable dq into the electric current equation for a complete formula. This separable differential equation provides the apparent current through a capacitor over a function of time. Let's rearrange the formula to solve for voltage instead of current. Since charge is the total amount of current passing through a point over a certain amount of time, it's represented here as the infinite sum of currents passing through the point with respect to time. This formula is essential for any calculation regarding capacitance and is also important in gaining an understanding of other formulas where capacitors interact with other passive circuit elements. To revisit the original question, the capacitor will receive a voltage of 50 volts. Note that since the current is constant and doesn't vary as a function of time, we can simply integrate by multiplying by t. This means that for any constant values, the equation simply returns a linear function. This function works well for any direct current source, and that's great, it's what it was designed to do. The problem is that the equation doesn't allow us to deal with multiple circuit elements. If a resistor and a battery were instead connected to this circuit, its current would be modeled by Ohm's famous equation V equals IR. This is a problem because its current limit depends on the voltage drop across it. Since the voltage of the capacitor changes with time, it'll impact the voltage drop across the resistor and thus its current output. In our example circuit, as the capacitor charges, the voltage potential across the resistor decreases, and thus the current into the capacitor does as well. This indicates that the charge function will follow a nonlinear curve, as the slope of the graph depends on the remaining voltage difference between the source and the capacitor. In order to find a relationship between the voltage of the capacitor, initial battery voltage, and resistance value, we can use Kirchhoff's voltage law, or KVL, in our simple circuit model. According to KVL, we know that the algebraic sum of all voltage differences around a closed loop is 0. From this, we can construct the following equation, assuming the capacitor is uncharged. Next, we'll solve for the voltage across the capacitor as a function of time. We'll call this function Vc of t. We know that the voltage across the resistor is just equal to its current times the resistance, and we know that the current through the resistor is equal to the current through the capacitor due to Kirchhoff's current law. Since the formula for electric current through the circuit is equal to the change in charge divided by the change in time, and we know that the change in charge is equal to the capacitance times the change in voltage, this can be inferred. Rearranging the equation into the standard form for differential equations, we get this. A first-order ordinary differential equation is called homogeneous if it can be written in this form. However, in this case, the equation is non-homogeneous, meaning that the solution will involve a particular solution due to the presence of a non-zero right-hand term, which is the voltage of the battery. In order to solve this equation, we first need to solve the homogeneous part of the equation. We can perform basic algebraic manipulation by dividing both sides by RC. Now that the equation is in the standard form for separable differential equations and all constants are on the right side, we can integrate both sides. Both constants can combine to form 1 because a constant minus a constant is still a constant. And to find Vc of t, we need to exponentiate both sides with the base e. Recall that the sum of powers is equal to the multiplication of powers with the same base, thus we can do this. Since e is constant, e to the power of a constant is still constant, and thus we get this. If we set time to equal 0, the function will collapse to this. This suggests that the constant k represents the initial capacitor voltage. Let's call it V0. What's left is simply an exponential decay function, which demonstrates the natural discharge rate of a capacitor. In fact, this models a circuit if we were to exclude the battery. The particular solution, or non-homogeneous solution, allows us to include a forcing function that represents an external input drawing the function to a certain value. In this case, it's the battery, which continuously adds energy into the system and determines what the function will approach after infinite time passes. Our original equation models the circuit with no external inputs or forces, simply an initial voltage. By solving the particular solution, we can find a function that models the external forces of the circuit, which can then be combined with the homogeneous solution to find a general equation. To solve the particular component, we can rewrite the full equation. We know that Vb is practically constant, as the battery voltage doesn't change much in regard to the size of the capacitor, so we can assume this. Therefore, we can ignore the derivative, and we're left with this. Usually the particular solution is much more difficult than this, but since we're dealing with a constant and not a function of x, it's much simpler. To obtain the final general solution, we can add both solutions together. At time t equals 0, the equation turns into this, because at the beginning the capacitor is uncharged, and thus algebraically, the voltage of the capacitor is equal to the inverse of the battery voltage due to KVL. This means that we can factor out the variables out of the equation and be left with a final one. However, graphing this function yields a function that never quite reaches the original charging voltage, and this is true. In an ideal world, capacitors never truly reach their maximum voltage. This is where the practicality of the time constant reveals itself. The equation for the RC time constant is this. Here the time constant is represented by the Greek letter tau, and represents the amount of time it takes for the capacitor to reach a voltage potential of approximately 63.2% of the supply. To understand why we use this method of measurement, let's find what Vc of t is equal to if we set t equal to Rc. The function simplifies to this, which can be further reduced to this. And this is where the 63.2% number comes from. It's the voltage that the capacitor reaches after Rc seconds have passed. The time constant is more often used in rough physics calculations because it's much easier to use simple formulas than to solve exponents every time you're working on a large circuit. In theory, a capacitor charging in a simple RC circuit approaches its maximum voltage asymptotically. This means that it never truly reaches the full charging voltage in finite time, but it gets closer and closer as time progresses. However, a general rule of thumb is that after 5 time constants, the capacitor is considered effectively charged, as it reaches about 99.3% of the charging voltage. Now, these equations can be applied to all sorts of situations involving modeling time circuits, but I would also encourage you to physically explore the behavior of capacitors and resistors. I find that it can be very easy to get caught up in all the maths without truly conceptualizing what all the formulas mean. After all, these equations are found almost everywhere in electronics, so it's essential you get them under your belt. Thanks for watching.